14 billion years ago, something impossible happened. Everything that exists, every galaxy, every star, every atom in your body, erupted from a single point smaller than the period at the end of this sentence. We call it the Big Bang, the ultimate origin story of our universe. But here's the paradox that unsettles even the brightest minds. What if the Big Bang wasn't the beginning at all? What if it was just one chapter in a story that stretches back before time itself? A story of colliding dimensions, cosmic cycles, and universes bubbling into existence from nothing. The deeper we look into the cosmos, the more it seems like the Big Bang is less of a starting point and more of a doorway. And what lies on the other side of that doorway may be stranger, darker, and more incomprehensible than anything we've ever imagined. The problem begins with something physicists call the singularity. If you rewind the universe backwards, galaxies rushing together, stars collapsing inward, everything compressing into tighter and tighter space, you eventually reach a point of infinite density and infinite temperature, a place where all the laws of physics break down. To scientists, infinities are red flags. They aren't answers, they're errors. Signs that the math we rely on to describe reality has completely broken down. Einstein's general relativity, which so elegantly explains gravity and the curvature of space-time, throws up its hands and quits at the singularity, and that means the very concept of the beginning may not be real in the way we think it is. Even more unsettling is what this implies about time. According to standard cosmology, time itself began with the Big Bang. Before that moment, there was no before, no space, no vacuum, not even emptiness, just nothing. But our minds recoil at this idea because everything in our experience has a cause, a sequence, a story that comes before. To say the universe simply appeared from nowhere, with no trigger, no context, and no reason, feels less like science and more like magic. And so scientists have pushed further, digging into quantum mechanics, string theory, and gravitational mathematics to ask the forbidden question: if the Big Bang wasn't the first moment, then what came before? The answers they've uncovered are as wild as they are profound. Some theories suggest the Big Bang was actually a bounce, the rebound of a previous universe that collapsed in on itself only to explode outward again. Others propose that our cosmos was born from the collision of higher dimensional brains, vast sheets of reality that slammed together in a realm beyond our perception. Still others hint that the Big Bang was a quantum fluctuation, a bubble of space-time foaming up from a sea of nothingness, one bubble among countless others, each expanding into its own universe with its own laws of physics. There are even theories that every black hole in our universe could spawn a new cosmos on the other side, making the Big Bang not the beginning of everything, but just the latest in an infinite chain of cosmic births. What makes all of this even more intriguing is that we're no longer limited to speculation. Powerful telescopes and gravitational wave detectors are giving us clues: fossil patterns in the cosmic microwave background, faint ripples in space-time, strange alignments in the oldest light in the universe that hint at a history older than the Big Bang itself. The more we measure, the more evidence we find that our universe may carry scars, echoes, or fingerprints of events that happened long before what we think of as the beginning. And here's the twist. Exploring what came before the Big Bang doesn't just tell us about the past. It may reveal our future. Because if the universe has bounced before, it may collapse and bounce again. If it was born from a collision, another collision may be inevitable. And if our cosmos is just one bubble in an infinite multiverse, then the reality we experience is only one version of countless others. The Big Bang is not a closed book. It's a door cracked open onto an infinite library, and we've only just begun to read. When scientists talk about the beginning of the universe, they often describe it as if we could simply press rewind on reality, running the cosmic film backwards. Galaxies drift closer together, stars collapse into dense clouds, planets dissolve into their elements until everything condenses into a single, unimaginable point. This is what physicists call the singularity, the place where the story of the Big Bang begins, or more accurately, where our mathematics stops working. At the singularity, all of space and time collapse into infinite density, infinite curvature, and infinite temperature. And if there is one thing physicists hate, it is infinity. Infinities in equations don't mean you've discovered something profound. They mean your model has broken down completely. Imagine trying to cram every human being on Earth into a box the size of a sugar cube. At some point, the concept itself collapses because matter has limits to how tightly it can be compressed. Now scale that thought up to the entire observable universe, trillions of galaxies, each with billions of stars, and squeeze all of that into something smaller than the tip of a needle. That's what the singularity suggests, and it should already sound absurd. Einstein's general relativity, the best tool we have for describing the warping of space and time, works flawlessly in most situations. It explains orbits, predicts black holes, and describes the expansion of the universe itself. But when applied to the very beginning, it reaches the singularity and simply breaks. It's like a calculator trying to divide by zero. Instead of giving a coherent answer, it flashes error. What makes this problem even more unsettling is that it isn't just about compressing matter, it's about the collapse of time itself. At the singularity, time doesn't exist in any meaningful sense. There is no before, no causal chain, no sequence of events. To ask what came before the Big Bang is, in this picture, like asking what's north of the North Pole. The question itself seems meaningless because the coordinates simply don't apply. And yet everything in human thought and experience rebels against this idea. We are creatures of cause and effect. We need beginnings and endings, stories that unfold with clear origins. To accept that the universe simply began without a cause feels not like science but like surrender. This is why the singularity problem haunts physicists. It suggests that the very laws we rely on to understand reality are incomplete. Somewhere deeper beneath general relativity, beneath the quantum mechanics that describes subatomic particles, lies a more fundamental truth that we haven't yet uncovered. Some physicists believe that this truth may come from unifying relativity and quantum mechanics into a single theory of quantum gravity. Others suspect that the singularity isn't real at all, but a placeholder for our ignorance, a flashing red warning sign that says, you've reached the limits of your understanding. And yet, this breakdown is not just a failure, it's also a doorway. Because when physics fails, it creates space for new ideas. If the singularity is impossible, then maybe the universe never actually shrank to a point of infinite density. Maybe something else happened at that moment. Maybe the Big Bang wasn't truly the beginning, but a transition from something that came before, something hidden behind the veil of our current equations. This is where the search begins, not just to understand how the universe expanded, but to uncover what, if anything, existed before time began ticking. And the deeper we look, the stranger those possibilities become. If the singularity is where our understanding collapses, then the search for answers forces us to zoom in even further, into the most extreme depths of reality. Imagine peeling back the fabric of space itself, magnifying it smaller and smaller, far beyond the scale of atoms, beyond protons and neutrons, beyond even quarks and the particles that dance at the heart of matter. Eventually you reach a place so small, so unfathomably tiny, that the very concept of smooth space breaks apart. This is the realm known as quantum foam, the smallest possible scale of reality, where space and time themselves are no longer solid, but frothing and turbulent, like a stormy ocean. It is here, many physicists believe, that the true story of what came before the Big Bang begins. At distances smaller than what's called the Planck length, about 10 to the power of 35 meters, space-time is not smooth and continuous. Instead, it bubbles and churns like boiling water on a stove. The calm fabric we take for granted at human scales dissolves into something chaotic and alive, a place where virtual particles constantly pop into existence and vanish in less than a trillionth of a trillionth of a trillionth of a second. To give you a sense of scale, if you blew up an atom until it was the size of the entire solar system, the quantum foam would still be smaller than a grain of sand within it. That's how deep into reality you have to dive before you reach this strange underworld. And here's where it gets truly unsettling. This chaos isn't just theoretical. Scientists have measured indirect evidence of it through experiments like the Casimir effect, where two metal plates placed unimaginably close together in a vacuum are mysteriously pushed toward each other. That push doesn't come from nothing. It comes from the restless bubbling of the quantum foam itself, the tiny energy fluctuations of empty space exerting pressure. What this means is that the vacuum of space is not empty at all. It is seething with energy, a hidden storm of creation and annihilation happening everywhere, all the time, invisible to us but absolutely real. Now imagine this foam not as a background detail of the universe, but as the very seedbed of reality. Many physicists suspect that before the Big Bang, before space and time as we know them existed, the quantum foam was already there. It may have been eternal, bubbling endlessly, producing tiny fluctuations, most of which vanished almost instantly. But every once in a while a fluctuation could grow instead of collapsing, like a soap bubble expanding from the froth of a bathtub. One of these quantum bubbles could inflate into something vast, and if it expanded rapidly enough, feeding on its own energy, it wouldn't just be a bubble, it would be an entire universe. Our universe. This idea transforms the Big Bang from a unique event into something more like a transition. Instead of space and time beginning from nothing, they could have emerged from this deeper layer of quantum reality where nothing is never truly empty. The bubbling sea of quantum foam may be the primordial canvas upon which universes are painted, and if it happened once, it could happen again and again and again, spawning countless universes, each born from the restless fluctuations of this cosmic ocean. This is the doorway through which modern cosmology steps after the singularity problem. If infinity is impossible, then perhaps what lies at the beginning is not a singularity at all, but a frothing, timeless sea of potential, where creation is not an exception, but the natural consequence of quantum chaos. And the more we study it, the more it seems that the Big Bang may have been just one bubble in an endless storm. If the quantum foam provided the spark, then inflation was the explosion that turned that spark into the blazing fire of a universe. According to the standard model of cosmology, in the tiniest fraction of a second after the Big Bang, less than a trillionth of a trillionth of a trillionth of a second, something extraordinary happened. The universe didn't just expand, it ballooned outward faster than the speed of light, growing from smaller than a proton to something the size of a grapefruit almost instantly. This event is called cosmic inflation, and without it, the universe we see today would make no sense at all. Inflation explains why the cosmos looks so smooth and uniform, why galaxies are distributed the way they are, and why the oldest light we can observe, the cosmic microwave background, appears so eerily, even in every direction. It was inflation that stretched out the wrinkles of the newborn universe, smoothing chaos into order. But while inflation solves many puzzles, it also creates some of the deepest mysteries in physics. To understand the problem, picture balancing a pencil on its tip. In theory, it's possible, but in practice, the slightest disturbance sends it toppling over. Inflation is like that. For it to work, the universe needed a special kind of energy field. Physicists call it the inflaton field, that had to be set up with almost impossible precision. Too little energy, and inflation would never have started. Too much energy, and inflation would never have ended, leaving the universe to expand forever without cooling enough to form stars and galaxies. The conditions had to be tuned so perfectly that some scientists describe it as walking a cosmic tightrope. How the universe managed to achieve this balance is one of the greatest unsolved mysteries in science. The strange thing about inflation is that while it explains what we see today, it doesn't explain itself. What triggered it? What stopped it? And why did it happen in exactly the way needed to produce a life-friendly universe like ours? The math suggests that inflation requires such delicate conditions that the odds of it happening by chance are vanishingly small. And yet here we are, in a universe that clearly went through inflation. Some physicists argue this points to the existence of deeper rules, something beneath inflation itself that made the process inevitable. Others go further, suggesting inflation may not be unique to our universe at all. Instead, it could be a repeating process, happening again and again across an endless landscape of universes, each one inflated into existence from the chaotic foam of quantum reality. And here is where the story begins to bend into the truly mind-bending. Inflation, in some models, never fully ends. While our local region of space cooled and slowed down, allowing galaxies and stars to form, inflation elsewhere might still be raging, creating bubble universes one after another in an infinite chain. In this picture, our Big Bang wasn't the beginning of everything, but just the local birth of one universe among countless others. This is the seed of what's known as the multiverse, the idea that our universe is just one bubble floating in a vast cosmic foam of endless creation. And the possibility that inflation itself is eternal raises a haunting question. If universes are constantly inflating, spawning infinite variations, then how special is ours really? But even if we set aside the multiverse, the problem remains. Inflation worked too perfectly. The universe we observe is balanced on a knife's edge, smooth enough to be stable but irregular enough to allow galaxies, stars, and eventually life to form. It is as if the early universe was programmed with extraordinary precision. And the deeper physicists study it, the more it looks like inflation isn't just a random accident, but part of a larger cosmic story we are only beginning to glimpse. Some theories propose that before our inflationary phase, space itself went through cycles of expansion and contraction, fine-tuning the conditions until they were just right. Others suggest that inflation was triggered by interactions between dimensions beyond our perception, like invisible forces pulling strings behind the curtain of reality. What we do know is that inflation took the universe from quantum chaos to cosmic order, from a frothing storm of energy to the structured stage upon which galaxies, stars, and life could one day appear. It smoothed, stretched, and balanced the fabric of reality in ways that continue to baffle scientists. And if it happened once, it may not have been the first time. Which leads us to a darker, more haunting idea that the universe may not have begun with a bang at all, but with a bounce. If inflation tells us how the universe expanded, cyclic or bouncing theories try to explain what came before. The idea that the cosmos began from nothing with no cause and no prior state is so unsettling that many physicists have searched for alternatives. And one of the most compelling possibilities is that the Big Bang wasn't a beginning at all, but a rebound. Instead of a singular creation event, the universe may be part of an eternal cycle of expansions and contractions, like a cosmic heartbeat pulsing through infinity. In this picture, the universe grows for billions of years, stretches out into a vast expanse, and then, under the pull of gravity, slows down, reverses, and collapses back inward. But instead of vanishing into a singularity, the collapse reaches a minimum point and bounces back outward again, triggering what we call a Big Bang. Our cosmos would then be just one phase in an endless series of births, deaths, and rebirths. The attraction of this idea is that it avoids the problem of infinities. Instead of compressing everything into a point of infinite density, the bounce imposes a limit. Space-time, according to theories like loop quantum gravity, cannot be crushed into nothingness. It has a smallest possible unit, like the threads of a fabric. When the universe contracts, those threads resist being compressed beyond their minimum size. At the point of maximum compression, a repulsive quantum force kicks in, reversing the collapse and causing a violent rebound. The result is a new expansion phase that looks to us like the start of everything. But in truth, it is simply the continuation of an eternal rhythm that has been going on forever. What makes this theory even more compelling is that it could explain some of the patterns we see in the cosmos today. The cosmic microwave background, the faint afterglow of the Big Bang, is almost perfectly smooth, but it also contains slight irregularities, tiny temperature variations that seeded the galaxies we see today. Some cyclic models predict that traces of previous universes could leave imprints in this background radiation, subtle echoes of earlier cycles. These would appear as unexpected alignments, unusual symmetries, or repeating patterns that shouldn't exist if our universe truly began from nothing. And intriguingly, when scientists study the cosmic microwave background in extreme detail, they do find anomalies, strange cold spots, odd alignments, mysterious patterns that some interpret as possible scars from a universe before ours. But the most mind-bending aspect of a cyclic universe is what it implies about time. In each contraction phase, as the universe shrinks, the flow of time may not behave the way we expect. Some models suggest that time could reverse, running backwards as the universe collapses, events that to us seem irreversible, stars burning out, galaxies drifting apart, could in some sense rewind, leading into the next bounce. From our perspective inside one expansion cycle, we would never notice this reversal. But at the deepest level of reality, time might not be a straight line from past to future. Instead, it could be a loop, endlessly repeating itself in cycles far grander than anything we can imagine. Of course, cyclic theories raise their own questions. If the universe has been bouncing forever, why does it look so fresh and ordered today? Wouldn't entropy, the tendency of systems to grow more disordered, eventually grind down the cycles into nothing but chaos? Some physicists argue that each bounce effectively resets the clock, wiping away the disorder of the previous cycle and starting anew. Others propose that dark energy, the mysterious force driving the universe's current acceleration, may eventually weaken, allowing gravity to take over and pull everything back together. Either way, the cyclic model offers something the singularity cannot: a universe with no true beginning, only eternal renewal. To think of the Big Bang as just the latest heartbeat in an infinite cosmic pulse is both unsettling and strangely comforting. It means our universe is not unique, but part of an endless lineage stretching backward and forward through eternity. And it suggests that death is never final, even on a cosmic scale. Galaxies may burn out, stars may collapse, but in the grand rhythm of the cosmos, every end is only a prelude to a new beginning. If this is true, then the universe we know is just one verse in an endless song playing out across cycles of unimaginable scale. But not all scientists believe in the comfort of repetition. Some argue instead that our universe was born not from its own collapse, but from a catastrophic collision in a higher dimensional reality. A crash so violent, it created space and time itself. If the idea of a bouncing universe is strange, then brain cosmology takes us even further into the unknown, into a realm of hidden dimensions and collisions, so vast they make even the Big Bang look small. In string theory, one of the most ambitious attempts to unify all of physics, the universe isn't limited to the 3 dimensions of space and 1 of time that we experience every day. Instead, reality may have additional dimensions, curled up so tightly we can't see them directly, or spread across a higher dimensional space that contains our universe like a page in a cosmic book. Within this framework, our universe could be what physicists call a brane, short for membrane, an enormous 3-dimensional surface floating in a higher dimensional arena called the bulk. Everything we know, every particle and force we can detect, is confined to this brane. We are trapped within it, unable to perceive what lies beyond. But just as pages in a book can lie side by side, there may be other branes drifting near ours, parallel universes stacked in higher dimensions, invisible but real. And this is where the theory becomes explosive. According to some versions of brain cosmology, our Big Bang was not the birth of everything, but the aftermath of a collision between 2 branes. Imagine 2 massive sheets of space-time drifting silently through the higher dimensional bulk. For eons, they float apart, unaware of each other, until gravity or some deeper force draws them together. When they collide, the impact releases unfathomable amounts of energy, enough to create all the matter and radiation of a new universe. From our perspective, trapped inside the brane where the collision occurred, it would look like a sudden, violent explosion, the Big Bang. What makes this idea so compelling is that it explains some of the universe's most puzzling features. One of the great mysteries of cosmology is why the universe is so flat and uniform on large scales. The brane collision model naturally smooths out irregularities because the enormous impact between branes wipes the slate clean, ironing out chaos into a nearly perfect state. It also hints that our universe may not be unique. If branes exist, they can collide not just once, but over and over, in a cosmic cycle of crashes and rebirths. Each collision creates a new universe, each with its own physical laws, its own galaxies, its own possibilities for life. We may be living in just one chapter of an infinite saga of brane collisions, one universe among countless others, created in the eternal dance of higher dimensional space. And the most tantalizing idea of all is that we may have a cosmic twin. When 2 branes collide, they both experience the impact, meaning 2 universes can be born side by side from the same event. Our cosmos may have a sibling universe, created in the same fiery collision that gave birth to ours, forever hidden in the higher dimensions, but connected to us in ways we don't yet understand. Some physicists speculate that the mysterious dark matter in our universe, the invisible substance that outweighs normal matter by a factor of 5, could be the gravitational influence of matter in this twin universe bleeding through from the other brane. If that is true, then the invisible scaffolding that holds our galaxies together may not even belong to our universe at all, but to another world drifting beside us, unseen yet profoundly connected. The mathematics of brane cosmology also predict something testable. A violent brane collision would send shockwaves through space-time, ripples that could leave imprints in the cosmic microwave background. These would appear as unusual patterns, circles, rings, or alignments that deviate from the randomness expected by traditional Big Bang theory. And while the evidence is still debated, some scientists believe they have already detected anomalies in the cosmic background radiation that might be hints of such a cosmic collision. To imagine our universe as the byproduct of a higher dimensional crash is both humbling and terrifying. It means that our existence is the debris of an accident in a realm beyond our perception. It also means that another collision may one day come, slamming brains together again and resetting everything we know. Whether this would happen trillions of years from now or whether it has already happened countless times before, the implication is clear. The Big Bang may not have been the first impact, nor will it be the last. But if brain cosmology explains what triggered the bang, another theory tries to answer what prevented the universe from collapsing into an impossible singularity in the first place. That theory takes us down to the very threads of reality itself, into the loops of space-time. If brain cosmology imagines universes colliding in higher dimensions, loop quantum gravity brings the focus back to the very foundation of space-time itself. At its core lies a radical idea: space is not continuous. It is not a smooth fabric that can be stretched infinitely thin, but something granular, woven from tiny loops at the Planck scale, far smaller than anything we can directly observe. Just as matter is made of atoms and light is made of photons, space itself, according to this theory, is quantized, built from indivisible building blocks that form a vast cosmic network. These loops are unimaginably small, but together they weave the geometry of reality, creating the illusion of smoothness when viewed from afar. And this simple shift in perspective changes everything about the beginning of the universe. In general relativity, space-time can be curved without limit. Compress matter and energy enough, and you create a singularity, a point where density and curvature go infinite. But in loop quantum gravity, that is impossible. The loops that make up space can only be compressed so far before they resist, like a spring that pushes back harder the more you squeeze it. At the point of maximum compression, instead of collapsing into a singularity, the universe rebounds. What we call the Big Bang in this picture was not the creation of everything from nothing, but the bounce that followed a previous universe's collapse. The implications are staggering. If loop quantum gravity is correct, then time did not begin 14 billion years ago. Instead, the universe has existed forever, contracting and expanding in an eternal cycle of bounces. Each collapse squeezes space to its minimum size. Then the loops of reality push back, triggering expansion again. Our Big Bang was simply the latest rebound in an infinite sequence, stretching back into eternity. The singularity vanishes, replaced by a cosmic heartbeat of contraction and renewal. This theory also offers potential clues we can look for. A bouncing universe should leave imprints on the cosmic microwave background, subtle correlations in the radiation patterns that reveal a pre-Big Bang phase. Instead of random fluctuations, we would expect to see hints of recycled information, echoes from a universe that came before. Some cosmologists believe we may already be seeing these signatures in the anomalies detected by satellites like Planck, though the evidence remains uncertain. If confirmed, it would mean we are literally seeing across the boundary of the last cosmic bounce into the ashes of a universe that lived before ours. But loop quantum gravity also raises profound philosophical questions. If the universe has no beginning, if time stretches infinitely in both directions, then the story of creation is not a single event, but an endless cycle. Every galaxy, every star, every life form has emerged before, in some form, and may emerge again. We are not the first universe, nor the last, but one verse in an eternal song, replayed with slight variations across infinite epochs. This vision strips away the finality of creation, replacing it with a kind of cosmic immortality. Death itself, at least on the scale of universes, becomes just another transition, another turn in the wheel. And yet, even as it removes the singularity, loop quantum gravity deepens the mystery. What causes the bounce? Why does the universe expand after compression rather than remaining frozen? And most importantly, what determines the laws of physics that govern each cycle? Are they fixed forever, or do they shift from bounce to bounce, producing universes with different possibilities each time? These questions remain open, but one thing is clear. If loop quantum gravity is right, then the Big Bang was not the first heartbeat of reality, only the latest. And that means our universe may not be unique at all. It may be just one ripple in an infinite ocean of cycles, endlessly collapsing and rebounding in the grand rhythm of eternity. But what if cycles and loops are not the whole story? What if our universe is not just part of an eternal rebound, but one bubble in a vast sea of universes, endlessly created in a process that never ends? That is the promise and the unsettling implication of eternal inflation. If the idea of a bouncing cosmos feels infinite, eternal inflation takes that infinity and stretches it into something even harder to grasp. In the standard picture, inflation was a brief, explosive event that happened in the first fraction of a second after the Big Bang, expanding space faster than the speed of light and smoothing out the cosmos into the ordered universe we see today. But what if inflation never fully stopped? What if it is still happening right now, in regions of space far beyond our view, endlessly creating new universes in an eternal chain? This is the startling implication of eternal inflation. Our universe is not the only one, but just one bubble in an infinite multiverse, born in a process that has no beginning and no end. Imagine a pot of water boiling on a stove. As the water heats, bubbles form, grow and detach, each one containing its own little pocket of vapor. Now replace the water with the quantum vacuum, the energy field that underlies space itself. In eternal inflation, space is like that boiling water, constantly expanding at unimaginable speeds. Within this expansion, bubbles form, regions where inflation slows down and cools, allowing matter, radiation, and galaxies to emerge. Our universe is one such bubble, but the boiling never stops. Even as our bubble expands, new ones are forming elsewhere, endlessly, forever. The result is an infinite froth of bubble universes, each with its own Big Bang, each expanding into its own cosmos, isolated from the others by the ever-growing sea of inflating space in between. What makes eternal inflation so powerful is that it naturally explains the fine-tuning of our universe. The physical constants in our cosmos, the strength of gravity, the mass of the electron, the value of dark energy, are balanced so perfectly that even a slight change would make life impossible. In a single universe, this looks like an incredible coincidence. But in a multiverse, it becomes inevitable. If infinite universes exist, each with different laws of physics, then some will inevitably have the right conditions for stars, planets, and life. We live in one of these rare universes, not because it is special, but because it is the only kind we could possibly exist in. Eternal inflation also reshapes our understanding of time and beginnings. If new universes are constantly forming, then there was no true first universe. Inflation stretches infinitely into the past and into the future, with bubbles forming forever in both directions. Our Big Bang was not the beginning of everything, only the local start of our particular bubble. Beyond the horizon of what we can see, other universes are inflating into existence right now, some older than ours, some younger, some unimaginably different. In some, gravity might be stronger, stars might burn hotter, or atoms might not exist at all. In others, there could be civilizations pondering the same questions we ask, unaware that their universe is just one bubble among countless others. And while these universes are hidden from us, some scientists believe they may leave traces in our own cosmos. If our bubble ever collided with another in the early stages of expansion, it could leave scars in the cosmic microwave background, strange circular patterns or unusual temperature alignments that break the uniformity. Researchers are actively searching for such signatures, hoping to catch a glimpse of our universe's neighbors in the multiverse sea. If such evidence is found, it would mean we are not alone, not even at the level of entire universes. The multiverse is both awe-inspiring and deeply unsettling. It suggests that every possible universe exists somewhere, every possible history plays out in some bubble, every possible version of you is living a different life in another cosmos. In an infinite multiverse, nothing is truly unique, not even our own existence, and yet this idea also offers a strange kind of hope. If universes are infinite, then beginnings and endings lose their finality. The death of our universe, no matter how cold or empty, would not be the end of reality, only the end of one bubble in an endless sea. In the multiverse, creation never stops. The Big Bang wasn't the beginning, it was just one of countless beginnings happening forever, everywhere. If eternal inflation paints the universe as an endless froth of bubbles, then black hole cosmology shifts the stage inward, suggesting that every universe might be born not from vast expanses, but from the very objects we consider the most destructive. Black holes are usually thought of as cosmic prisons, regions where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse under their own weight, squeezing matter into a point of seemingly infinite density, surrounded by an event horizon, the ultimate point of no return. From the outside, they appear to be dead ends, swallowing everything and giving nothing back. But from another perspective, they may be the very wombs of new universes. The mathematics of general relativity suggests that the interior of a black hole is not a singularity in the usual sense, but a new region of space-time. To an observer falling in, space might not end. It might expand. The crushing collapse that forms a black hole could, under the right conditions, ignite a new cosmos on the inside with its own space, its own time, and its own laws of physics. From within, it would look like a Big Bang. From without, it would look like a simple black hole. This leads to a stunning possibility. Our universe itself may be the interior of a black hole in some larger parent universe. The connection is not just poetic, it's mathematical. The black hole, with the mass of our observable universe, would have an event horizon roughly the same size as our cosmic horizon, the boundary beyond which we cannot see. That symmetry suggests a deep relationship between black holes and the universe itself, as if the structure of reality is recursive, repeating itself across scales. Every black hole in our universe could contain its own baby universe, and our universe could be the child of another, part of an infinite lineage of cosmic generations. If this is true, it also explains why our universe is fine-tuned for complexity. Universes that produce many black holes would naturally produce many offspring. Over countless generations, universes with the right physical laws to create stars and therefore black holes would dominate the cosmic family tree. In this view, the reason our universe allows for galaxies, planets, and life may be the same reason it produces black holes efficiently. Universes that can create black holes are the ones that survive. This is cosmic natural selection, with black holes as the reproductive organs of the multiverse. And there's more. If every black hole creates a new universe inside, then every universe contains countless others. The supermassive black hole at the center of our galaxy, millions of times more massive than our sun, may house a universe of its own, with galaxies, stars, and perhaps even intelligent beings who see their cosmos as vast and ancient, never realizing it lies inside a black hole in our sky. From their perspective, their universe is as real as ours. From ours, it is invisible, sealed away by an event horizon. The structure of reality could be a nesting doll of universes within universes, each black hole a portal to another creation. This idea also changes how we think about the end of our universe. If our cosmos is a black hole in a larger space, then its eventual evaporation through Hawking radiation would not be an end, but a transition, returning information to the parent universe, while new universes continue to blossom inside. Death and birth become inseparable. Destruction becomes creation. The most violent objects in the cosmos may, in fact, be the most fertile. But if black holes can give birth to universes, then another possibility emerges. Maybe our reality is not as real as it feels. Maybe the three-dimensional world we live in is just a projection of information stored on the surface of a cosmic horizon, like a hologram. If black holes suggest universes within universes, the holographic principle pushes the idea even further, questioning the very nature of reality itself. It begins with a paradox. According to classical physics, when matter falls into a black hole, it is lost forever. The information describing its properties, its structure, its composition, its history should vanish beyond the event horizon. Yet quantum mechanics insists that information can never be destroyed. This clash between gravity and quantum theory drove physicists to a radical solution. The information doesn't disappear into the black hole at all. Instead, it is preserved on the surface of the event horizon, encoded in 2 dimensions, like a cosmic storage device. The black hole may look 3-dimensional, but everything that falls in is written on its boundary. And from this revelation comes an even stranger conclusion. The same may be true for the universe itself. The holographic principle proposes that everything we perceive as 3-dimensional reality, the galaxies, the stars, the planets, the air we breathe, even our own bodies, is actually a projection. Just as a 2-dimensional hologram on a sheet of film can produce the illusion of a 3-dimensional image, the entire universe may be a 3-dimensional illusion, projected from information encoded on a distant 2-dimensional boundary. Our cosmos, in this view, is a grand hologram, its depth and solidity nothing more than emergent properties of underlying data. This idea is not just philosophy, it emerges directly from mathematics. Calculations show that the maximum amount of information contained in any region of space is proportional, not to its volume, as we might expect, but to the area of its boundary. Double the radius of a sphere, and the number of bits of information it can hold increases by a factor of 4, not 8. Reality, it seems, is written on surfaces, not volumes. If applied to the entire universe, this means that all of the information needed to describe every star, every galaxy, and every particle could be encoded on the distant cosmic horizon, the boundary of the observable universe. We live inside the projection of that information, experiencing a world of apparent depth and solidity, while the true reality is far thinner and more abstract. What's remarkable is that experiments are already probing this possibility. If space-time is ultimately holographic, then it should be pixelated at the smallest scales, like the grain of a digital image. Subtle fluctuations, known as holographic noise, may appear in the fabric of reality, detectable by ultra-sensitive laser interferometers designed to measure minute distortions in space. Early experiments have hinted at anomalies that could be consistent with this noise, though nothing is yet conclusive. If confirmed, it would mean that space itself is not continuous, but a coded projection, a cosmic film being played on the boundary of reality. The philosophical implications are staggering. If the holographic principle is true, then everything we consider fundamental: space, time, matter, even consciousness, might not be fundamental at all, but emergent phenomena arising from information. The universe would be less like a physical stage and more like a vast computation unfolding across a cosmic screen. What we call reality would be nothing more than the shadow of something deeper, something mathematical and abstract. And yet, this does not make life meaningless. If anything, it expands the scope of existence. Information is indestructible. Even if stars burn out, galaxies collapse, and the universe itself decays, the information that encodes reality endures on the cosmic boundary. Nothing is ever truly lost. What we call the Big Bang might not have been the birth of space and time at all, but the moment when information began projecting a new holographic reality. In that sense, before the bang, the universe already existed as information waiting to be played. But if reality is a projection, we are left with a haunting question: who or what is the projector? And is our holographic universe just one among many, each written on a different boundary, each casting its own shadow of existence into the infinite? If the holographic principle suggests reality is an illusion projected from information, quantum tunneling takes us deeper into the bizarre possibility that universes can emerge from nothing at all. In the strange world of quantum mechanics, nothing is never truly empty. Even in the vacuum of space, particles are constantly flickering into existence and then annihilating, borrowing energy from the void in accordance with the uncertainty principle. Space is alive with possibility, a restless sea of fluctuations that never stand still. And in this landscape of probabilities, something astonishing can happen. Entire universes can spontaneously appear. This phenomenon is called quantum tunneling, the process by which particles manage to cross barriers they have no right to pass. Imagine rolling a ball up a hill. If it doesn't have enough energy, it should roll back down. But in the quantum world, the ball can sometimes appear on the other side of the hill without ever having gone over it, as though it tunneled straight through. This strange behavior, confirmed countless times in experiments, suggests that probability rules reality at the smallest scales. And if particles can tunnel into new states of existence, perhaps entire universes can as well. Some physicists believe the Big Bang itself was the result of quantum tunneling. Before our universe, there may have been nothing, no space, no time, no matter, no energy. But nothing in the quantum sense is not an absolute void. It is a state of potential, a field of possibilities where even the absence of reality contains the seeds of creation. In this timeless quantum vacuum, a fluctuation could have tunneled into existence, creating a tiny bubble of space-time. That bubble, fueled by inflation, exploded outward to become our universe. From the outside, if such a perspective even makes sense, this would have looked like something appearing from nothing, a spark flashing into being without cause. From the inside, it would look like the Big Bang, the sudden emergence of a vast and expanding cosmos. What makes this idea so compelling is that it solves the puzzle of energy. The total energy of our universe appears to be zero. All the positive energy of matter and radiation is balanced by the negative energy of gravity, perfectly cancelling out. This balance makes it possible for a universe to emerge from nothing without violating conservation laws. It would be like creating a bank account with a positive balance and a matching debt. The net total is still zero, but activity exists nonetheless. In the same way, our universe could have sprung from a quantum fluctuation because the books of cosmic accounting balanced perfectly. But quantum tunneling raises profound questions about meaning. If universes can emerge spontaneously without cause or design, then our cosmos may not be unique or intentional. It may be one of countless universes that bubble into being and vanish again, most collapsing back into nothingness almost instantly, a few surviving long enough to evolve into stars, galaxies, and conscious observers. We happen to live in one of the rare successful universes, not because it was chosen, but because we could not exist in the others. This idea also blurs the boundary between physics and philosophy. What does it mean to say that a universe came from nothing? If nothing can fluctuate, is it truly nothing at all? And if universes are constantly tunneling into existence, then our Big Bang was not a unique miracle, but one instance of a cosmic process that may be happening endlessly across an infinite quantum landscape. The mathematics of quantum cosmology even suggests that these universes can exist in superposition, overlapping in a strange quantum state, where every possible history is realized. In this view, before the Big Bang, the universe did not simply not exist. It existed in every possible form at once, a wave of probabilities waiting to collapse into the reality we inhabit. Consciousness itself may have played a role in selecting which version became real, collapsing the cosmic wave function into the universe we know. Quantum tunneling forces us to confront the most unsettling possibility of all, that existence requires no cause, no creator, no plan. The universe may simply be because, at the deepest level of quantum reality, existence is inevitable, nothingness is unstable, and out of its instability comes creation. The Big Bang was not the beginning of everything. It was the moment when the potential hidden in nothingness chose to become something. If quantum tunneling hints that universes can spring from nothing, cosmic natural selection suggests that universes don't just appear randomly, they evolve. This radical idea treats the cosmos not as a static creation, but as a living process governed by rules similar to biological evolution. Just as life adapts and reproduces through natural selection, universes themselves may reproduce, mutate and compete, with the most fertile universes dominating the multiverse across endless generations. It is a vision of reality where universes beget universes, where the cosmos itself is a self-sustaining organism, and where our universe is just one offspring in a vast and ancient family tree. The mechanism for this reproduction may lie in black holes. In many theories, the formation of a black hole does not end with a singularity. Instead, the collapse may trigger the birth of a new expanding region of space-time on the other side of the event horizon. From our perspective, the black hole simply swallows matter and disappears. But from within, a new universe may ignite, with its own Big Bang, its own physical laws, and its own cosmic history. Each black hole, then, becomes a reproductive organ of the universe, a cosmic seed from which new universes sprout. This is where natural selection enters the picture. Just as living organisms pass traits to their offspring with slight variations, parent universes may pass their physical constants to child universes, but with small mutations. The gravitational constant might be slightly stronger or weaker, the masses of particles slightly different, the value of dark energy shifted. Most of these variations would produce sterile universes, incapable of forming stars, galaxies, or black holes. But some variations would prove successful, generating conditions favorable for black hole production. These universes would reproduce prolifically, creating more and more offspring, in a cosmic version of Darwinian competition. Over time, the multiverse would become dominated by universes optimized for black hole formation. This perspective sheds new light on the mystery of fine-tuning. The constants of nature in our universe seem remarkably balanced to allow complexity and life. If gravity were a little stronger, stars would collapse too quickly. If weaker, galaxies would never form. The balance seems so precise that many have wondered if it requires design or purpose. But in the cosmic natural selection model, the answer is simpler. Our universe is fine-tuned not for life, but for black holes. Life exists as a side effect of the conditions that maximize black hole production. And since universes that make black holes outcompete those that don't, the fact that we find ourselves in a universe filled with stars and galaxies is no accident. It is the natural result of cosmic evolution. The implications are staggering. Our universe, in this view, is not the first but the latest in a long lineage of universes stretching back through countless generations. Each universe inherits traits from its parent, modified slightly, and passes them on to its children. The Big Bang was not the beginning of everything, but the birth of an offspring in an evolutionary process that has been running for eternity. We are not living in a random cosmos, nor one crafted for us, but in a successful universe that survived and reproduced because its laws favored the formation of black holes. And yet, the story does not end there. If universes can evolve, then intelligence itself may one day influence the process. Advanced civilizations may learn to create black holes deliberately, seeding new universes and imprinting them with chosen conditions. In this way, cosmic evolution could transition from blind natural selection to guided reproduction, with conscious beings shaping the destiny of universes themselves. It is a vision where life is not a byproduct of cosmic evolution, but its driver, and where intelligence may ultimately participate in the creation of entire realities. If cosmic natural selection is real, then the multiverse is not just an ocean of random universes, it is a dynamic, evolving ecosystem. And our Big Bang was not a singular miracle, but the latest birth in an endless lineage of cosmic ancestors. The universe we see around us may carry the fingerprints of generations past, and the future of existence may rest in the hands of life itself. If cosmic natural selection imagines universes reproducing like living organisms, the simulation hypothesis pushes the boundaries of imagination even further, suggesting that the universe itself might not be a natural system at all, but an artificial construct, a vast digital simulation running on an incomprehensibly advanced form of computation. At first, this might sound like science fiction, the premise of a movie or a thought experiment. Yet, as technology advances and our own ability to simulate increasingly complex realities improves, the question grows harder to dismiss. What if our reality is not the base layer, but a programmed environment, the creation of an intelligence beyond our comprehension? The idea begins with a simple observation. In only a few decades, humans have gone from primitive computer graphics to highly detailed virtual worlds where millions of players can interact in real time. The characters inside these worlds follow consistent laws, inhabit complex environments, and make choices that appear meaningful. If technology continues to advance exponentially, it is not hard to imagine simulations so advanced that the beings inside them would experience their world as fully real. They would look up at their skies, build their sciences, and ask about the origins of their universe, never realizing that everything they perceive is information rendered by a processor. If we can imagine this for our own technology in the near future, what could be possible for a civilization thousands or millions of years more advanced? Philosopher Nick Bostrom sharpened this idea into a formal argument. He suggested that if advanced civilizations are capable of creating simulations of universes, then they might run many of them, for research, for entertainment, or even for preservation. If each advanced civilization can produce countless simulations, then the number of simulated universes would vastly outnumber the one base reality. Statistically, it would be far more likely that we are living in a simulation than in the original universe. In this framework, the Big Bang was not the ultimate birth of reality, but simply the initialization of a simulation, the moment when the system booted up and began running the code that generates everything we see. Evidence for this possibility is subtle but intriguing. The laws of physics themselves resemble computer code. Reality appears quantized, broken into discrete units at the Planck scale, as if space and time themselves are pixels in a cosmic screen. The mathematical structures underlying physics are eerily precise, as though they are algorithms governing a simulation. Some researchers even suggest that if we probe deeply enough into the fabric of space-time, we might find evidence of computational limits, like the grid lines of a video game world when the resolution is stretched too far. Cosmic rays, for example, might reveal anisotropies, preferred directions that betray an underlying lattice structure to the universe. The simulation hypothesis also offers answers to some of the greatest mysteries of cosmology. Why are the physical constants so perfectly tuned for complexity and life? Perhaps because they were programmed that way, chosen by the creators of the simulation. Why does the universe appear finite but unbounded, expanding as if space itself is being generated in real time? Perhaps because the simulation renders only what is necessary, generating space as needed, just as a video game engine creates environments only when players move into them. Why does quantum mechanics appear probabilistic, with particles existing in multiple states until observed? Perhaps because the simulation saves resources by running outcomes as probabilities until an observer forces the system to resolve into one definite result. This vision is both exhilarating and unsettling. If true, it would mean that everything we know, our history, our sciences, even our sense of free will, exists within parameters set by programmers we cannot perceive. Yet it also raises a more profound question: does being simulated make our reality any less real? For the beings inside a simulation, their experiences are genuine, their emotions authentic, their questions meaningful. Whether base reality or simulated, life is still lived. Choices are still made, meaning is still created. The simulation hypothesis also suggests that the cycle of universes might be recursive. If civilizations within simulations eventually create simulations of their own, then reality could be an endless stack of nested simulations, each one believing it is fundamental, each one perhaps separated by only a line of code from the one above. Somewhere beyond all the layers, there may exist an original universe, but it may be so far removed from us that its nature is forever unknowable. And yet, even in this dizzying vision, one fact remains constant: consciousness. Whether base or simulated, reality is experienced through awareness, through the act of asking questions and seeking answers. Perhaps the true mystery is not whether the universe is natural or artificial, but why consciousness exists at all to perceive it. If the simulation hypothesis is correct, then the Big Bang was not the first explosion of matter and energy, but the flick of a switch, the moment someone or something pressed run on the code that became us. Speculation about what came before the Big Bang is captivating, but science thrives not on imagination alone, but on evidence. Theories about bouncing universes, multiverses, holograms, or simulations all remain fascinating possibilities, yet their value lies in whether they can make predictions that can be tested. And remarkably, many of these bold ideas do leave fingerprints, subtle traces etched into the cosmos that scientists are actively searching for today. The universe, if studied carefully enough, may hold the clues we need to determine whether these grand visions are fantasy or fact. One of the most promising avenues of evidence comes from gravitational waves. These ripples in space-time, first detected in 2015 when two black holes collided, are now a thriving new branch of astronomy. But beyond these recent events, physicists are hunting for a more ancient signal: primordial gravitational waves generated in the first instance of the universe, or even before the Big Bang itself. Different pre-Bang theories predict different patterns. A bouncing universe would produce waves with a distinctive frequency spectrum reflecting compression and rebound. Eternal inflation would leave a background hum of waves from bubble collisions in the multiverse sea. Brane collisions in higher dimensions would imprint entirely new polarization signatures. These signals would still be echoing across the cosmos, and next-generation detectors, including space-based observatories with laser arms millions of kilometers long, may one day catch them. If found, they would act like fossils from before time itself, carrying direct evidence of what came before the universe we see. Another cosmic laboratory lies in the oldest light we can observe, the cosmic microwave background. This faint afterglow of the Big Bang is a near-perfect uniform bath of radiation, but hidden within it are tiny fluctuations, temperature differences of millionths of a degree that encode the conditions of the early universe. Satellite missions like WMAP and Planck have mapped these fluctuations with astonishing precision, but scientists are still analyzing them for anomalies. Some theories predict specific repeating patterns or alignments that could only be explained by pre-Big Bang physics, such as cycles of contraction and expansion or collisions with other universes. Already there are strange cold spots and alignments in the microwave background that standard cosmology struggles to explain. Whether these are random flukes or the first hints of something deeper remains one of the great open questions. Particle physics offers another potential window. The discovery of the Higgs boson in 2012 confirmed that our universe rests in a delicate balance of quantum fields. But calculations suggest that this balance may be metastable, like a ball perched on a plateau that could one day roll into a deeper valley. This points to the possibility of vacuum decay, where our universe could tunnel into a new state of physics. High-energy experiments may reveal whether our universe truly sits on such a precarious foundation. If so, it would mean the Big Bang might have been triggered by a similar vacuum transition in some larger reality, giving us experimental hints about what preceded our cosmos. Even the search for extra dimensions offers testable predictions. If string theory is correct and hidden dimensions are curled up within space, then high-energy particle collisions could reveal their presence through missing energy signatures, particles suddenly vanishing into dimensions we cannot see. Similarly, experiments designed to measure gravity at microscopic scales are probing whether it weakens unexpectedly at short distances, which would be a clear sign of hidden dimensions leaking force away. If confirmed, such findings would revolutionize our understanding of what space itself is and how universes can be born from higher dimensional structures. Perhaps the most mind-bending tests come from the holographic principle and the simulation hypothesis. If reality is holographic, then space-time should exhibit a kind of pixelation at the smallest scales. A jittery holographic noise, ultra-sensitive interferometers, originally built to detect gravitational waves, are now being used to hunt for this fundamental graininess of space. And if we are living in a simulation, then there may be detectable limits to the resolution of reality, energy thresholds, or anomalies in cosmic rays that reveal the digital lattice underlying the universe. So far, no definitive signs have been found, but the search continues, and the very fact that such ideas are testable makes them part of legitimate science rather than pure speculation. The true test of these theories may come not from a single discovery, but from convergence. If gravitational waves, cosmic background anomalies, particle physics results, and space-time measurements all begin to point toward the same story, we may finally glimpse the truth about what came before the Big Bang. And if we do, it will mark a turning point in human history, the moment when we realize that our universe is not an isolated accident, but part of a larger structure, a deeper process, or even a designed simulation. The evidence is out there waiting to be read. The challenge is whether we will build the tools and summon the imagination to decode it. In the face of theories about multiverses, bouncing cycles, holograms, and simulations, it is easy to feel overwhelmed, even insignificant. After all, What weight does one human life carry against an endless sea of universes, each potentially birthing and dying in cycles that span trillions of years? From one perspective, we are microscopic, less than a blink in cosmic time, a fragile species clinging to a pale blue dot orbiting an ordinary star. And yet, when we reflect more deeply, the very fact that we are here to ask these questions transforms the story. Consciousness, awareness, and the ability to wonder about the cosmos infuse existence with meaning that sheer size and scale cannot diminish. In fact, one could argue that consciousness elevates the universe itself, for without awareness, the cosmos would be silent and blind, vast but unobserved, existing without recognition or reflection. The history of science has often humbled humanity. We learned that Earth is not the center of the universe, but one planet orbiting one star among hundreds of billions. We discovered that our galaxy is just one among trillions, drifting in a universe so immense it defies comprehension. Now, modern theories suggest our entire universe may be one bubble among infinite others, or even a simulation written by a civilization beyond our imagining. And yet, there is another way to see it. Every discovery that makes the universe feel larger also highlights the uniqueness of our ability to comprehend it. Rocks and stars cannot question their origins. Galaxies cannot reflect on their place in the multiverse. But we can. The universe has given rise to beings who are not only made of stardust, but who can look back on the stars and ask why. This shift in perspective reframes significance. Importance is not measured by size or duration, but by depth of awareness. A fleeting flame can illuminate darkness more profoundly than an eternal void. In that sense, humanity's ability to ponder the Big Bang, to imagine realities beyond our own, and to design experiments that peer into the first instance of creation makes us an extraordinary expression of the cosmos. We are the part of the universe that has become self-aware. The atoms forged in ancient stars have arranged themselves into brains capable of asking about the stars themselves. This feedback loop, matter questioning its own origins, may be one of the most remarkable phenomena in existence. Theories about what came before the Big Bang often suggest endless cycles, infinite possibilities, or realities so vast they make our universe look small. But rather than making life meaningless, these possibilities can inspire awe. If there are infinite universes, then the emergence of beings who can think, dream, and love becomes even more extraordinary. If our cosmos is one of countless others, then the fact that conditions aligned to create life here makes our reality a precious rarity. And if the universe is a simulation, then our capacity for authentic experience, joy, curiosity, sorrow, love, proves that reality is not diminished by its origins. Simulated or not, lived experience is real to those who live it, and that is what gives it weight. Perhaps the deepest significance lies not in what came before the Big Bang, but in what we do with the time we have within this universe. The cosmos may be infinite, but our lives are finite. The universe may span eons, but we each receive only a brief moment of awareness. That moment, however, allows us to create meaning through our actions, our relationships, and our pursuit of knowledge. We are participants in a story that began long before us and will continue long after, yet what we contribute during our chapter matters not to the cosmos in some grand accounting, but to one another and to the unfolding of consciousness itself. Human significance in the cosmic story is not about scale. It is about perspective. Against infinity we may seem small, but within awareness we are vast. The Big Bang may not have been the beginning, and the universe may not be the whole of reality, but for us here and now, it is the stage upon which meaning unfolds. And in that we are not insignificant at all. We are the universe, awake and reflecting on itself, adding something precious to the grand eternal story. The journey through the mystery of what came before the Big Bang leaves us with more questions than answers, yet that is precisely what makes the pursuit so powerful. Each theory, whether it is the eternal cycle of expansion and collapse, the infinite sprawl of the multiverse, the strange mathematics of holograms, or the unsettling possibility of simulation, pulls back the veil a little more on the greatest enigma of all existence itself. The Big Bang was not just the origin of matter and energy, it was the beginning of time, the birth of the very stage on which events unfold. To ask what came before is to press against the limits of human thought, to challenge the very foundation of cause and effect. And yet, even as these questions push us into realms that strain logic, we continue to pursue them, because the act of asking is what defines us as conscious beings. What we have discovered so far is that reality is stranger than common sense allows. Time may not be a continuous river, but a quantum fabric stitched together from discrete moments. Space may not be smooth and infinite, but granular, pixelated at the smallest scales, as though woven from threads of information. Universes may not be solitary but prolific, giving birth to one another through black holes, vacuum transitions, or higher dimensional collisions. Even the most radical possibility that everything we experience is code running on a cosmic computer does not diminish reality, but reframes it, showing us that what matters is not the source but the experience itself. These possibilities, as wild as they sound, are grounded in serious physics, mathematics, and observation. They are not idle fantasies, but attempts to reconcile the paradoxes that arise when we push our theories to their extremes. Yet, the conclusion of this journey is not to say that one theory is correct and the others are wrong. We do not yet know whether the universe bounced, tunneled, or was simulated into being. What we know is that the evidence is building, that gravitational waves, cosmic background radiation, particle accelerators, and quantum experiments are beginning to probe questions once thought beyond reach. In the coming decades, we may find hints that tilt the balance toward one explanation, or perhaps discover that reality is a fusion of many ideas, more complex than any single model suggests. Science advances not by providing final answers, but by refining the questions, by turning mysteries into puzzles we can solve. And through it all, one truth stands unshaken. Our existence is part of this cosmic story. We may be small in scale, but in awareness, we are immense. The universe has given rise to beings who can look back across billions of years, who can contemplate cycles spanning trillions, who can imagine infinities upon infinities. That act of reflection itself is a miracle. The atoms forged in stars, arranged by chance and physics into the complex structures of life, have become aware of themselves, capable of asking not only how the universe began, but why anything exists at all. In that sense, we are not passive observers. We are the universe experiencing itself, the cosmos awake, questioning its own origins. The conclusion, then, is not a final answer, but an invitation. The mystery of what came before the Big Bang may never be fully solved, or perhaps the answer is so strange that our current minds can only glimpse it in fragments. But the pursuit itself is the point, to wonder, to search, to build instruments that listen to the echoes of creation, to craft theories that stretch imagination to its breaking point. This is what makes our species extraordinary. The Big Bang may have been a transition rather than a beginning. But for us, the search to understand it is a beginning of its own, a beginning of wisdom, of humility, and of awe. We stand at the edge of knowledge, staring into the darkness before time, knowing that the answers may always slip beyond our grasp. And yet, even if we never find them, we have already transformed the silence of the void into the poetry of inquiry. That is our triumph. In the end, the question of what came before the Big Bang is less about uncovering a final truth and more about embracing the endless journey of discovery. The universe is vast, ancient, and perhaps infinite, but through our awareness it has found a voice, and that voice will keep asking, keep seeking, and keep wondering for as long as it exists.